Welcome to Ask and Learn.
In this problem, we have a well-insulated rigid vessel containing saturated liquid water. Electrical work is then done on the water, and we have to calculate the final temperature. We assume that the tank is stationary, and thus the kinetic and potential energy changes are zero. The thermal energy stored in the tank itself is also negligible. So, if we take the contents of the tank as the system, this system is closed since no mass enters or leaves the boundaries. So the energy balance equation can be written E in minus E out is equal to delta E, the change in energy of the system. Now we only have the energy in due to the electrical work being done in the system, and this is equal to the change in internal energy in the system, delta U. So we can write delta U as M into U2 minus U1. Now that's our energy balance equation. So the first thing we can do before we can apply that equation is we can find the electrical work done on the system. So the amount of electrical work done in 30 minutes, we calculate by using the equation VI delta T. The potential difference V times the current I times the change in time delta T, which is essentially the power times time. So the voltage is 50 volts, the current is 10 amperes, and the time is 30 minutes. So that's 30 times 60 seconds. And we get the electrical work done on the water to be 900,000 joules or 900 kilojoules. Now we can go to our initial state and find the properties, namely first the specific internal energy U1. Remember, this is a saturated liquid. So if we go to our tables, that's UF at 40 degrees Celsius. And this is 167.53 kilojoules per kg. The initial specific volume of the system V1 is equal to Vf, also at 40 degrees Celsius. And again, from our tables, this is 0.001008 cubic meters per kg. Now we can go back and substitute this into our energy balance equation, and we get that the electrical work done into the system is equal to, remember, M into U2 minus U1. So if we rearrange this equation, we can find the internal energy at the final state, U2. This is U1 plus the electrical work done into the system over M. And so this is equal to 167.53 kilojoules per kg plus the electrical work done 900 kilojoules over the mass of water, which is 3 kg. And so we get specific internal energy at the final state to be 467.53 kilojoules per kg. Now that we have the internal energy at the final state, we can go to our tables and look for the final internal energy that corresponds with 467.53 kilojoules per kg and a specific volume V2, which is the same as volume V1, and that's 0.001008 cubic meters per kg. So we cannot find this temperature directly from the steam tables at the end of the book, but if we approximate the final compressed liquid state as a saturated liquid at given internal energy, then we can determine this from one of our tables. But since we have our internal energy and our specific volume, this corresponds to a temperature T2 of 118.9 degrees Celsius.